Hello, everybody. Very happy to be here back in Bengaluru for Current. And I know it's the worst slot of the day to be in. I know you have, hopefully had a great conference. I guess the energy is a bit low. I'm standing between you and your very well-deserved evening drinks. So I hope this will still be a worthwhile and useful session to you. And to kick things off, well, I've been working on event-driven systems and change data capture and all that good stuff for quite a few years. And there's this one thing which comes up again and again, and this is what's called dual writes. So essentially the idea of doing two things, like writing to a database and then accessing Apache Kafka, for instance, to do those two things at once without actually having transactional guarantees around this. And I will explain why this is a problem and what we can do about it. So this is the idea for this talk. At some point, I came up with this logo or slogan there. Friends don't let friends do dual writes. And we even put it onto a t-shirt. They're kind of like a collectible item now. And I realized, I guess I could have ironed the t-shirt for taking the picture, but you get the idea. So this motivates the talk, right? So this is a problem, dual writes, and there's actually a solution to that, and this is what I want to talk about. And unfortunately, there's so many articles and resources, also on very well-reputed sites out there, which still make you believe you could do this. And actually, I'm here to tell you, no, you cannot, and what is the alternative instead? So I want to talk a little bit about what's called the Outbox pattern. So this is really the idea for this talk, because the Outbox pattern, it's a solution to those problems. So I want to start and bring everybody to the same page so we all know what this is about, what is the problem, and how the Outbox pattern can help us here. I want to touch a little bit on some of the implementation details. How can we go and build a reliable and safe Outbox implementation? And I want to discuss it, because, I mean, this has been around for a while, so maybe there are better alternatives by now. Maybe there's other things to look at this problem. And this is also what I want to touch on in this talk. I work as a technologist at Confluent, just joined there a couple of weeks ago, so still very new into the job. I hope I still say Confluent, or I say Confluent when I talk about my employer. You know, I still have to get used to it. In my past life, I used to be the project lead for a project which is called Debezium, which is a tool for change data capture. So who has heard about Debezium? So that's, very good. So like 2/3, maybe even 3/4, very good. Who is using Debezium in production? Okay, this is like the brave quarter. Very good. Amazing to hear that. So, so this is why you might know me. There's a few other things like Casey Cuttle, a command line client for Kafka Connect, and a few other things I've been involved with over the years. All right, so let's get at it. What is this problem with dual writes? What is it, what we want to solve here? And it's a task, a situation which we have commonly, very often, when we build, in particular, microservice architectures, right? Because the idea is, well, we want to decompose our business problem into loosely coupled, highly cohesive services. But the thing is, they don't exist in isolation, right? They still need to cooperate, they need to collaborate. So they need to exchange information and data and messages between each other to all come together as a distributed system to solve a particular task. And as we implement such an architecture, very often we are confronted with this task that we need to update the state which exists in the database of our own service, say MySQL database, a Postgres database. So we want to go there and update state there, right? Like persist a purchase order, update a customer record, and so on. And at the same time, well, we are part of this distributed system, ecosystem of microservices. We want to tell other services that something has happened. And now those two things, they need to happen at once. They need to happen, in particular, atomically, right? So what we really don't want to afford is we do the one thing, we update our database, but then for whatever reason, we don't get to do the other thing, tell the other services, because then our overall system state would be inconsistent, and we don't like inconsistency, right? So that's the problem. And now, it's a common task, right? I guess everybody, as you work on those kinds of applications in your day jobs, you will encounter this sort of situation. And now, let's come back to this idea of dual writes, because it seems so easy, so attractive on the surface to just go and do this. And now you could go to your browser and you could do web search and you would probably see this sort of approach proposed to you many, many times, and still it's not the right thing to do. So on the surface, what you could do is, well, I will just do those two things, right? I will just go to my database, update some data there, and then if I want to talk to those other services, maybe I want to decouple them, so I put in the middle something like Apache Kafka to have like replayability, a durable commit log, all this good stuff. And it looks nice on the surface, but the problem is those two things, writing to a database, sending a message to Kafka, as of today, they cannot happen transactionally. So there is just not a way right now that Apache Kafka could participate in a distributed transaction, which means we are prone to those problems, right? So let's say this write to our database, it succeeds, our transaction gets committed, and then for whatever reason, we cannot talk to Kafka, there's a network split or whatever. Now we have a problem, right? Because our overall system state is not consistent. So we have, let's say, updated or persisted this purchase order in our database, but we didn't get to tell the shipment system about this new purchase order. And now maybe this customer is waiting because, well, we committed here, so we told the customer who gave us this request, we will have your order, but we never get to tell the shipment service about it, so it would never be fulfilled. Or it could happen the other way around. So maybe because you think, okay, if I cannot do that, so let me try and turn things around. Let me first write to Kafka and then do my database write. Well, the same thing could happen. So now you have told the shipment service, and maybe they will go and fulfill this order, but you in your own database, in your order services database, you don't know about this order. And I guess that's even worse because you have sent out a product to a customer and you don't know about it. So that's pretty bad, right? And now, no matter how you turn it, it's just not possible to do those things reliably, consistently, atomically, in the absence of distributed transactions. And if you are familiar with Kafka, you will know, as of today, Kafka cannot participate in distributed transactions. There's a KIP, a Kafka improvement proposal, which is about to change that. So at some point, this might actually be doable. And we may be able to do this sort of thing, because then Kafka could be part of a two-phase commit transaction. But even then, and I will touch on that later in the talk, I would argue it's not something which we probably should do. And I will explain later on why I think that's the case. Okay, no dual writes. So what else can we do? And this is now where this notion of the Outbox pattern comes into the picture. So the idea there is, well, I mean, we cannot reliably update those two resources, our database and Kafka, but we always can update a single resource, our database. I would make the case, if we have this service and we cannot write to our own database, something is very bad, right? So we will have a big problem. So I mean, this is our own state and our own system, so we need to be able to access it, right? Otherwise, we are in a big, big failure state. So the idea there is, okay, let's have our service write to its database. Let's say we have, this sort of e-commerce domain, tables like customer and address. We do our data changes there. And of course, this happens in a transaction, right? So all the writes to different tables, different records, they would happen in a single transaction. And now at the same time, within the same transaction, so one shared local transaction locally to this database, we also do an insert into what's called the Outbox table. So this Outbox table, this is essentially our messaging fabric, which we will use to send out messages to the outside world. As this is one transaction in our database, all this happens atomically in the transaction, so we have a strong guarantees, consistency guarantees, right? So if this transaction commits, then we will know we have done all those changes. So we have updated our internal data model, we have updated our customer address records, and we also got to insert into our Outbox table. Or if this transaction gets rolled back, for whatever reason, I don't know, maybe constraint violation, whatever it is, well, then all these changes would not happen, right? So this is happening atomically. Now, of course, the question is, well, writing into this Outbox table, this is good, this is nice, but it doesn't help us, right? So we still need to get this message out to our external consumers. And this is where another component gets added, which is called the Outbox relay. So this is essentially in charge of taking messages from this Outbox table and propagate them to the outside world. And we will discuss different options how this could be implemented. And then, well, typically this Outbox relay, it will not directly, let's say, call REST APIs in those external services, but rather it would go through some messaging infrastructure like Kafka or whatever else you would have there, just for the sake of being able to replay events, to set up more and more consumers down the road. So this is a very common architecture to have this Outbox relay and then send to Kafka and then have your consumers, like our shipment service, our whatever service it is, to subscribe to those events from this Kafka topic there. Okay, so let's talk a little bit about the structure of this Outbox table. And essentially, well, it's a channel for messages what you want, which you want to send. And the most important column there is on the right, this payload column. And as you see there, I mean, I used JSON there just to give you the idea. This could be anything, right? This is the data you want to send, the messages you want to send. Could be JSON, it could be Avro, protobuf, you name it. And also, the structure of the data, it could be whatever you want this to be, right? So this is essentially, it forms sort of a data contract between your application and the consumers of those messages. So you would, for instance, evolve the structure of this data in a backwards compatible way, right? So you would keep this very much in mind. Those messages and their schema, it forms a contract which you don't want to arbitrarily break, right? But again, it's a free-form structure, right? So it's whatever you want it to be. So that's the payload. And then typically you would find in this sort of Outbox table a number of further columns. Well, you would have something like an ID, which just identifies uniquely a message. So in this case, it's like a GUID, but it could be anything really. You would have something like an aggregate type. So here I'm using the language from the domain-driven design. So the idea is your business logic, it revolves around aggregates like customers, purchase orders, so like, you know, units of your data model, which for instance might be stored in multiple tables in your relational database, but they form one entire cohesive structure. And having this aggregate type there makes just sense because it allows you later on to route messages which pertain to different types, for instance, to different Kafka topics. So you could use this information and then send those messages which are representing purchase orders to a purchase order topic. And finally, we have this aggregate ID, which in Kafka terms we will use as the Kafka message key. And this is just there to make sure that all the messages, which for instance pertain to the same purchase order, 1, 2, 3, that in terms of Kafka, they would go into one single Kafka partition. So we have the correct ordering for all the messages for that particular purchase order or customer or whatever it is. And you could have more there, right? But this is like the foundational structure of an Outbox table, I would say. Okay, so now we have this data in our Outbox table. And I mentioned, well, we want to get those messages to our consumers, right? So we need to think a little bit about how to implement this Outbox relay. And there's like two fundamental options for doing that, I would say. One is polling, and the other one would be log-based change data capture. And I want to talk a little bit about both of them and what their trade-offs are. So polling. Let's say we have our Outbox table, and intuitively what we want to do there is, well, we need to go to this table and essentially identify the messages which we have not propagated yet, right? So essentially what you would do is you would add some sort of like a position field or like an offset in the table. So then you can go to the table and in this query, like you would do this every minute, every 10 seconds or whatever, so you could fetch all the messages from this Outbox table where the position is greater than the last one you had seen before, right? So this intuitively gives you the idea, okay, you know, whenever there's a new message in this Outbox table, I will be able to catch that and send it to my consumers. So on the surface, again, this looks fine. So if we have, let's say, this sort of, you know, flow of transactions, you know, 3 transactions, they happen maybe like concurrently, subsequently, and they insert messages at position 1, 2, and 3. And now we poll, and we get this result. So we also want to order, of course, by the position. So this works fine on the surface. And I also should mention, in this Outbox table, we only ever do inserts, right? So we would never go and update an existing Outbox record because this is an event which we send to our consumers. Events are immutable, so you would never update them. You would only ever append to this Outbox table. So you could think about it also like an append-only log in a sense. So now, again, there's some, the devil's in the details, right? So for instance, let's assume this sort of situation. Let's say we are using Postgres and we are using a database sequence to obtain the values for that position number. We could run into a situation which looks like this. So we have transaction 1, which starts before transaction 2 But then, depending on, this is a multi-threaded, a concurrent problem, so depending on the specifics of timing, it could happen we have the position 1 because we just fetched that sequence first in transaction 2, and then we get position 2 in transaction 1. We commit them, so the transaction 1 commits before the transaction 2. And now if we look at our Outbox table, we have it ordered by the position, but actually the order as indicated by a position, it does not represent the order of transaction execution. So actually what we have in this Outbox table there, it doesn't tell us the same picture as which exists in our internal data model. And now this could be a problem or it could not be a problem, depending on what is the nature of that data. But it could mean that essentially you give an inconsistent picture to your consumers because, again, it's not representing the transactions as they have been executed in your own data model. So that's one problem, ordering. And maybe we can work around it. But there's even a bigger problem lurking there, and this is we might actually miss events. And this might happen in a situation like this. We have those 3 transactions, again, they indicate like when do they start, when do they finish, and how we obtain our position value. And so let's say we poll once and we capture this first event. So we put this into our Outbox table, so that's good. And then a short later after, we have our next polling run, which happens in point of time where this red line is happening. So we know we have seen position 1 before, so we query now, we want to have all Outbox events which have a position which is greater than 1. Now the problem is this transaction 2, it hasn't committed yet. So we would not see this record from transaction 2. We would only see this one here, number 3. So we would go and insert this into our Outbox table. So we have there 1 and 3. And now, well, transaction 2 might actually commit. We run our polling loop again, but now we would query, okay, give us all events where position is greater than 3. So we would miss this event with number 2, which obviously is a problem because we are back into a situation where we don't send all the events out to the consumers. Now there is a way to work around this. Essentially what you can do, it depends a little bit on the database. You can skip all those messages which have been created after transactions which are still in flight. So essentially you can query for the state. So you could query, in particular with Postgres, where everything which is greater than position number 1, but also there should be no in-flight transaction which has started before this one. So you can detect the situation, but it also means if you have like long-running transactions, they would kind of block all the subsequent IDs. So this is my long-winded way of saying this is pretty delicate to get right, and the overarching problem with all this polling-based implementation, of course, is, well, how often do you want to do this, right? Do you want to query like every minute, every 10 seconds or whatever? So there's this trade-off between what is the overhead of this and what is the latency of this, and it's generally not an approach which I would recommend. So, luckily, there's an alternative, and this comes in the form of log-based change data capture, and in particular using Debezium, which so many of you are using already, which is good. So let's talk a little bit about this, and I just want to bring, again, everybody onto the same page. So the idea there is, well, instead of polling onto our tables, what we do is, well, we extract information, we extract data from our transaction log of our database. So every database has a transaction log, which is an append-only data structure which exists for the purposes of transaction recovery and also replication in a cluster. And now a CDC, change data capture tool, like Debezium, is able to extract the information from this transaction log and propagate this information to our external consumers. So this is what log-based change data capture is about, getting information from a transaction log and propagating it. And this now does not come with those problems, right? So we don't have any ordering issues here because, well, the transaction log, it has the information about our transactions and about the records which got changed in the order of transaction execution. And we also don't have this problem of missing any events, well, because this is the canonical source of our database, right? So if we go there, we can get all the events in the correct order and never will anything be missing. What I should mention is this now, of course, is eventually consistent, right? So we will send this out asynchronously to our consumers, but this is something which makes a lot of sense in this distributed system, right? Because this shipment system, it doesn't really need to have instantaneous visibility into our purchase orders, let's say. For a customer who puts in a purchase order into our order system, it doesn't really matter whether like 1 second or 2 seconds later, the message would then show up in our shipment system. So that's fine, but it's something I want to call out. So, Debezium, as I mentioned, is a popular open source implementation of log-based change data capture. Again, many of you know it already, so I just want to draw your attention to some of the newer things which have been added relatively recently. So there is this notion of incremental snapshotting. So those of you who use Debezium, they will know there are some challenges about backfilling events, like capturing the current state, because you cannot get everything from the transaction log if your database has been around for a while. So you would need to do this initial snapshot of data, and there's this very powerful notion of incremental snapshotting. There's a JDBC sync connector. So for a long time, Debezium was essentially known as a set of, in terms of Kafka source connectors, so which get data into Kafka. And now there's also actually a JDBC sync connector, which is very closely integrated, of course, with the source connector. So it understands the Debezium change event format. It can do a very good job in terms of reacting to particular data types, schema evolution, and so on. There's quite a few more things. You will find all those on the Debezium blog. The last thing, because it's just all the rage these days, there's also a WASM-based single message transformation now. So if this is your kind of thing, you can, for instance, use Golang to implement message transformations and then execute them as WASM within Debezium. So that's pretty cool, I would say. And then there's one other thing, one other bigger change which I want to mention, and this is the project right now is in the process of moving to an open source foundation. So as I mentioned, I used to work for Red Hat, and they are the main backers of the project. So they created it, they founded it, they employ many of the committers. And now they made the decision to contribute this project to what's called the Common House Foundation. So it's an alternative to foundations like the Apache Software Foundation, which just means it's even more interesting and attractive for people to communicate, to contribute to the project, to be part of it. And this is what I would very much invite everybody to do. So you can go, right now, for instance, what we are discussing is this governance structure, right? So how should the project governance look like? And everybody can bring their voice and opinion and be part of that community. So I think that's great news for the project, because it just allows many, many more parties and entities to come and all rally behind the project. Okay, let's get back to the Outbox pattern. So I guess you won't be surprised if I tell you there is actually first-class support in Debezium for implementing the Outbox pattern. So there is an SMT, a single message transformation, which essentially gets configured like this. So this is Kafka Connect configuration. So you say I have this transformation, which I call Outbox. It's using this particular type, the event router. And this essentially takes our raw Debezium change events, and again, it would only ever be inserts, and converts them into a structure which is a bit more friendly to consume for our downstream services. So how does this look like? Well, if we have here, and I hope it's large enough for the people in the back, but so this is how like a Debezium change event would look like, right? So we have this common structure with the before and the after part. Because this is an insert, there's only the after part, then it has those fields from this Outbox table, right? Which I mentioned before, like aggregate ID, aggregate type, and our payload here. And now, if I apply this transformation, this event router, it actually looks like this. So the payload field, so only the value of the payload field, this gets promoted to the sole content of the Outbox message. And then the Kafka message key, so this would be our aggregate ID. So aggregate ID gets promoted into the message key, so we have the correct ordering of all the events for the same aggregate, same purchase order, customer, and so on. And it also does this routing into different topics. So based on the aggregate type order, this would be sent into a topic called Outbox event order. You can customize the structure, but you get the idea. And then there's also a Kafka message header, so our original message ID, this gets promoted into a header property, so consumer could, for instance, deduplicate events. So that's the Outbox event router. Very useful thing to implement the Outbox pattern. Housekeeping. As I mentioned, we only ever do inserts into our Outbox table. And now if I've used Debezium to extract those inserts well, I could get rid of them again, right? Because I don't want this table to be ever growing. And the good news is, well, I can do this all in a single transaction. So I can do my insert and I can do my delete right away, because I still would have the insert and the delete in the transaction log, which is enough for Debezium to capture that insert event, right? So now if I were to go and take a look at this table, it would always appear empty, but still the information has been written to the transaction log, and you don't have to think about housekeeping. There's one alternative which I want to mention for, in particular, if you are in Postgres, because as I mentioned, this Outbox table, it's like an append-only log, essentially, right? So we are kind of abusing a table as an append-only log structure, even more so if we do the insert and delete in a single transaction, right? So it even makes this more apparent. And now, as it turns out, what Postgres lets me do, I can actually write directly to the append log of the database, the val, the write-ahead log. I can write arbitrary messages there using this function, pglogical emit message. And I would say this is a very nice alternative for implementing the Outbox table if you're on Postgres, because, well, then you don't even need to have a table. You just write those messages directly to the log. So here you would say, this is a transactional message. So, this should be committed or rolled back with transactions. So that's what the true stands for. You give it a type. So I want to say these are my Outbox messages. And again, it's an arbitrary structure which I'm writing there, right? And now only those messages, they would only show up in the transaction log. And I think that's very elegant. For MySQL, there's like a black hole table model which you could use to a similar effect. Okay, so let's talk a little bit more about some particular implementation details. So there is one thing about backfills. So as I mentioned, you might be in a situation where you need to recreate all the events for existing data, right? So I don't know, maybe you have misconfigured your Kafka topics, you have retention period too low, now your data is lost and you want to rebootstrap the entire state. And so Debezium by itself, it supports this with the notion of snapshotting, and we can do something similar for our Outbox events. I mean, it's a bit more of a hand-made process because, well, we want to have all those backfill events go into an Outbox table. So that, that's why we need to do this ourselves, but we can follow the same principles as what Debezium would do with regular tables. So the idea is, well, we have our service, our purchase order service, let's say, which writes the Outbox events for our ongoing transactions. And now at the same time, we want to backfill events for existing data. And of course, this is a concurrent, concurrently running task, right? So we have multiple processes which write to our Outbox table, like our service, our standard business logic, and our backfill process. So we need to make sure we don't have things like lost updates, for instance. And this is what we can do. So we would have our backfill component. And now the idea is, well, we want to essentially emit those backfill events. So they describe the current state of, let's say, all of our purchase orders. And of course, we want to deduplicate this with the events as they are written by our actual business logic. And in particular, we want to give precedence to all the events which are written by our service. And we only want to propagate a backfill event if we don't get an update or a regular Outbox event for the same purchase order or for the same customer. And this is what we can do with this approach. So essentially, what this backfill process would do, it inserts marker events into this Outbox table, this chunk start and chunk end events. So this gives us a windowed view onto our Outbox structure. And now within those chunk windows, it would do those backfill events. So I don't know, it would backfill all the purchase orders for a specific time range, for instance. So we have this, demarcated between those chunk start and chunk end events. And then we would apply some deduplication logic. So we would essentially look at one of those windows between those two markers, and then we would discard all those backfill events for which we have seen a regular Outbox event in the same window. So if this purchase order 123 actually has seen a standard Outbox event in this window, then we would discard the backfill event. And essentially we would only propagate those backfill events for IDs, for records which have not been modified within this window. So that's the high level intuition. And there is essentially, or what I should mention is this is based on a paper by some Netflix guys called dblog. So Netflix, at some point, they implemented their own change their capture framework. So they didn't go with Debezium. They implemented their own thing. And thankfully, they wrote this paper about this, what they call a watermark-based backfilling approach. So I highly recommend to check out this paper. It's very well written, very well digestible. And this is what backs the incremental snapshotting in Debezium and also this idea of which I just described. Let's change gears a little bit and let's go to our consumers. There's the aspect of idempotency there. So as I mentioned, all this happens eventually consistent and also typically with at least once semantics. So this means if there's like a failure, your Debezium connector doesn't stop clearly, it crashes for whatever reason, could happen, I don't know. You might receive duplicate, or a consumer might receive duplicate events when the pipeline gets restarted. And well, typically we want to identify and then discard duplicate events. So what you want to have is, well, you want to have a unique ID. And I had this GUID ID, this GUID there, right? Which identifies each and every event. So we could use this and keep track of all the events which we have seen in our consumer. And then if we receive another event which has the same unique ID, then we know it's a duplicate and we can discard it. The problem is, well, if I have those IDs, it's like an ever-growing state, right? Because I need to keep track of all of them. For how long should I keep track of them? So a better idea is to use a monotonically increasing value. So then I know, okay, if I have seen event number 100, and if I get then again an event with a lower ID like 99, I know, okay, this must have been a duplicate, so I can discard it. Now, as I mentioned before, we cannot use a database sequence for that, because if I have multiple transactions, it would not be guaranteed to be monotonically increasing. Instead, we would have to find another value, and this again depends a little bit on our database. So here, in case of Postgres, I can use what's called the LSN, the log sequence number, I believe. So this is now guaranteed to be monotonically increasing as our transactions get committed, and I can use this to detect the situation that I'm receiving an event which I have seen before, and I only need to store the latest LSN which I have ever seen, so just a single value and no ever-growing state. Okay, so Outbox pattern. We have spoken a lot about it. Now let's talk a little bit about it. And people, I mean, with everything, and I would say this gets used quite a bit. It's widely used. And with everything, I would say people have criticisms of that, right? And this is just fair. And I want to discuss two things. And the first one would be, well, does this not mean we create database overhead? And database overhead, typically people mean two different things by that. So one is, well, I might create more load on my database. And the other thing is, well, I might increase the state size, so the size of my transaction log. And I would say, well, this could be a problem, but I don't think in reality it is. Because let's talk a little bit about the load overhead. Well, if I execute my business transactions, I will probably write to many tables already. So I might do 5 or 10 or whatever inserts in my transaction already anyways. Now if I do an 11th insert into this Outbox table, I would say, in the grand scheme of things with transaction overhead and so on, it just doesn't really matter. There might also be overhead on the extraction side. So how do we get events out of our Outbox table? And there I would say, well, yes, if I do this polling-based approach and I run this polling query very often, this could be overhead. Whereas if I do the log-based CDC approach, this is very efficient. So typically people don't notice any impact on the database when they use a log-based CDC tool. So that's the one part. And then on the size of the val, well, or the transaction log more generally speaking, I would say again, in particular, if we do this, what I've shown you, like I do my insert and I might do my delete right away, or I just write, for instance, to the transaction log directly using this PG logical emit message function, well, then I don't really have any sustained overhead because all those elements which are in the val, they will be discarded relatively quickly, and it just doesn't matter. So I don't think in reality this is a problem. So I would say it's more like a theoretically existing problem, but then in practice I just have never seen it to be actually a problem. The other concern is, well, with this approach, don't we increase the end-to-end latency? So if I were to send directly a message from my order service to my shipment service, I would have lower latency, right? And again, yes, that's true on the surface, but I would argue it's not a problem because, well, I have decomposed my overall problem space into loosely coupled systems. And I would argue if I have done this job correctly, it just should not matter, if this shipment service sees a particular event a second earlier or a second later. And I'm very consciously speaking of seconds because if I do this log-based CDC approach, I can have end-to-end latencies which are sub-second, in the sub-second range. So again, I don't think this is a problem. Or the other way around, if I perceive this latency concern is a problem, then I would argue probably I have done this decomposition into services not the right way. Let's talk a little bit about alternatives. So is this Outbox panel still the right thing, or should we do other things? And I have a few things I want to discuss there. The first one would be, I could do the opposite of what I have described so far. So far, I did first my insert to my database, and then I sourced the writes to Kafka using our Outbox relay. I could have the idea, okay, let me do this the other way around. Let me write to Kafka first, and then, well, I probably want to take those events and put them into a local database so I can run queries because, well, I cannot query Kafka, right? So I would do this for my own service, and then I would take those events again and, have my external consumers subscribe to that. So this works, and I'm not saying it's necessarily a bad idea. There's one big caveat, and this is, well, all this happens, again, asynchronously, right? In particular, those writes into this local database, they also happen asynchronously. So you would lose what's called read your own writes, or in particular, synchronous read your own writes. So what could happen is your service receives a request to place a new purchase order, we write it to Kafka, and then we put it into our database. But the next second, I go to my service and I query this database for all my purchase orders, and I might not see it there because, well, this took, it's an asynchronous process. I just don't have any guarantees. And now this is a problem, right? So just think about it from user's perspective. You place your purchase order, like the next second you go to the list of all your purchase orders, and your order doesn't show up. So it's a weird user experience. And again, there's ways to work around this with caching and all this good stuff, but it just increases complexity. And also, if you want to think about things like how would you go and implement unique constraints with this sort of architecture, it can become very complex very quickly, and I would generally not recommend it. The other way, the next option would be, well, I mentioned in the beginning, Kafka is about to get support for two-phase commit transactions, right? So there's this KIP 939, it's work in progress right now, so at some point, this would be possible, and it might be an option. The thing is, it has an impact on the availability of your service, because now what you need to have in order for your inbound requests to succeed, you need to have those two resources available at once. So you need to be able to write to your database, and you also need to write to your Kafka cluster. And just by definition, the more resources you synchronously require, the lesser your overall availability will be, right? And again, I just don't think it makes that much sense to put it here, into my synchronous transaction execution phase, because this is like a downstream process in any case, right? So it just doesn't make sense, in my opinion, to use up the cycles I have for doing things in a synchronous way for doing that. So it will be possible, but again, it's probably not something which I would recommend to do by default. And the last option I want to mention is stream processing. So maybe we work on an application and it's a legacy application, it has been around, we cannot modify it or we don't want to modify it. I've worked in situations where we didn't even have the source code for applications anymore, so it was just a war file running on some Tomcat, nobody could ever go and modify it. This kind of stuff happens, right? Now what you could do there as well, you could say, okay, I actually use now a tool like Debezium to capture the raw changes from my actual tables, like customer address, purchase orders, and so on. I propagate them into Kafka, and then I use a tool like Apache Flink for stream processing to take those raw events and create like a higher level event representation, maybe denormalized, maybe filtered, whatever transformation you want to do. There is this notion of data contracts which lurks here in here, so you might be able to create a nicely separated view, which shields the consumers from the details of this internal data model. So again, it's a very valid option. You can do it. There's also some caveats here, in particular, if it's concerned around transactional consistency. So a tool like Debezium, it will capture all the events one by one, so there's not really a notion of transactionality in here, which means if you create those derived downstream events, they might expose intermediary state to your downstream consumers, which wasn't really visible as that in the source database. I'm working on some ideas for improving that, but again, it's quite tricky, and I would advise to be cautious of those. All right, so where are we at? Well, I mean, as with everything, and I think this is the most important takeaway for every talk really, there is no silver bullets. There is not the one way to do a thing, right? It's always about trade-offs. It's always about the semantics and details and characteristics of a specific situation, which then should inform the decision what you should do. So I'm not even saying you should never do a polling-based CDC approach. There might be situations where it is feasible to do that. Maybe you just don't have a log-based CDC connector for a particular database, so you cannot use Debezium. It could happen, right? So in this case, you might want to use a polling-based approach. But then again, if you can, I would always advise to use log-based CDC. Similarly, with all the alternatives we discussed, well, maybe it makes sense in a certain case to do stream processing and to have this pipeline of transforming your raw events into higher level externally facing change events. It could make sense, but then maybe doing this within the transactional scope of your source application, it's the easier thing. So it's really about trade-offs and understanding what makes the most sense in a particular situation. And I hope with this talk I could give you some ideas to inform those decisions. The one thing which I really want to recommend is use, if you can, I speak a lot about Postgres, right? Because I just really like it. It's, I guess, my favorite database, I don't know. So if you are there, I would recommend use PG Logical mid-message, to insert your Outbox events right directly into the transaction log. I think it's a very elegant and efficient way for implementing the Outbox pattern. Finally, coming back, most importantly, don't let friends do right? So this is really the number one thing. Don't do this thing which we have seen at the beginning. Just write to those two resources, a database and Kafka, and hope for the best, because hope is not a strategy, right? This is bound to give you headaches down the road. I've just seen it again and again. People assume it's fine on the surface, and then in the worst possible moment of time, they realize, oh, actually, I end up with inconsistencies, and now I have a bit headache, right? So this is really what you want to avoid. If you like, you can reach out to me. I have my new Confluent email address, so you can send me an email there. I'm on Blue Sky, I'm on Twitter. You can follow my blog. I have just written about some of the things I spoke about, so you check this out. And I think we have 1 minute and 30 seconds for questions. But first of all, thank you so much. Thank you. Any questions? Yes, there is one. I think we do have a mic, right? Yes.
Yeah, I wanted to mention just one more solution to the Outbox pattern which Oracle has implemented, because we have queues in the database. So the transaction Outbox pattern just becomes a local transaction. Because when you produce and consume, you're just doing database activity to tables. So queues are implemented as tables. So that's just another way to implement Outbox pattern.
Okay, so that's a comment, not a question, I guess. So yes, okay.
Just wanted to mention that.
Yeah, okay, no, that makes sense, yeah.
Hi, first of all, great presentations. It was like, I'm following your blogs also, so many of the things you already covered in blog. I have few questions on the best practices that you do with this, right? So first one is, like, how do you handle stream governance on this part? Like,
how do I handle what?
Stream governance on this part, like PI redaction,
right.
Schema evolution on that part.
Right.
Also, like, because we are also using the DBGM connector, writing to Kafka Confluent topic and then writing to Databricks. How do you suggest, like on this, like currently we are having a DBGM connector writing to dev, prod, and staging. All of them have their own service accounts, right? And then there is a soft limit on service account, like 1,000 on Confluent. So do you suggest having service account for each DBGM connector, or like having one service account and then handled by API keys in that way, right? And then, yeah, so these are the two.
Okay, I see. So about stream governance, yes, thank you so much. I mean, I happen to work for a vendor which can help you with that, so I think this is probably the domain of platforms like ours, but also many others, which provide you with the right tools for putting those mechanisms in place to make sure, who can access certain streams, certain topics, to have RBAC in place for that. So I think, look at the managed platform for that. I think the open source tools like DBGM, they provide the technical underpinnings for that, but typically they are not as strong when it comes to that. And about the second one, about service accounts and how to set this up, I guess I would need to know a little bit more about your specific situation. In general, what I would always recommend is to try to separate those environments as much as possible, right? So really ideally you have the same infrastructure in something like Terraform, in one place, and then you can apply it to different environments just by enabling the right environment, and then you would create separate service accounts, would create separate topics and everything. Maybe even use a separate account in your cloud platform to do that. So that would be my answer to that. Okay, so I think we're out of time. I will still be here to take some more. So I just don't want to stop people from going to the party. But I will be here, and I'm very happy to take more questions. Thank you so much.